Hi everyone, my name is Jabin George, and I'm here to talk about magnetic angiotrophy materials based magnetic particle imaging tracers. So monodispersed superparamagnetic nanoparticles have received great attention over the past several decades in its potential for many applications, specifically biomedical ones. With new emerging imaging modalities known as magnetic particle imaging, or MPI, its uses can be implemented in diagnostics and guided therapies. However, the issue that we face with implementing these modalities is a lack of control over physical and magnetic properties of tracers when implementing them into commercial processes. As a team, we have continued to develop novel biocompatible magnetic nanoparticles with maximized sensitivity and resolution. For many years, spherical nanoparticles have been used because of amorphous particles typically adopting to a spherical shape due to its microstructural isotropy. In Figure 1, different applications of magnetic nanoparticles are shown and the role it plays in. From MRI contrast agents to recording medias, magnetic nanoparticles can also be implemented into MPI applications, more specifically biomedical ones. With each application having a different function, the particle properties must be specific for that. In order to have a specific particle property for MPI applications, the synthesis of monodispersed iron oxide nanoparticles has to occur. And we do that by using solventless thermal decomposition procedures. This procedure synthesizes various shapes from spheres, cubes, octahedrons, multipods, nanowires, and nanorods, as you can see in Figure 2. Figure 3 shows the basic principles of MPI. MPI is an emerging imaging modality for multiple reasons, but mainly because it uses no ionizing radiation in the scanner or tracer, which makes it extremely safe when compared to other imaging modalities such as nuclear medicine, CT, and X-rays, which use the ionizing radiation. With the extended useful life of the tracer, MPI tracers, when developed, can last for long periods of time. MPI functions by having two magnets facing each other on the same side, creating a magnetic field. With transmit coils changing the direction of the field constantly, a field-free point emerges, and this is where particles can be processed by the technique of MPI. Any particles outside of this field-free point is saturated and cannot be scanned by MPI. Through the receiving coils, X-space and harmonics graph these images and provide an image reconstruction. In Figure 4, you can see that zero field-free cooled magnetization plots are plotted on a graph. And these show that the angiotrophic shaped nanoparticles, which are the nanowires, cubes, and octahedrons, show a better stoichiometry. In Figure 4b, the nanowires showed much higher signal intensity when compared to the spherical nanoparticles. But in Figure 5, that shows the MPI implications, iron oxide nanorods showed the highest signal intensity when compared to all other angiotrophy-shaped nanoparticles. Alongside this data, we found that magnetic nanorods at 70 nanometers showed high resolution and selectivity for MPI when compared to isotropic nanoparticles. Over the few years that MPI has emerged as an imaging modality, there has been a lack of studies related to the magnetization of nanorods on MPI. But as the applications of MPI grow from cellular tracking, perfusion, targeting, and drug delivery systems within a living organism, tracer development becomes more important in maximizing the efficiency of what magnetic particle imaging can possibly do. Now that the new data has shown that the strength of nanorod signals in MPI techniques, I believe we are going in the right direction of what MPI could become in biomedical applications. That is all. Thank you for listening. And again, thank you, Dr. Mohapatra and Dr. Liu, for helping and giving the opportunity to conduct and learn all these experiments and the mentorship.